Hello and welcome to the screencast, Modeling with Transformed Exponential Functions. So previously we've observed that if a quantity changes so that its growth or decay occurs at a constant percentage rate with respect to time, then the function is exponential. Many different natural quantities change according to exponential models. For example, money growth through compounding interest, the growth of a population of cells, or the decay of radioactive elements. A related situation arises when an object's temperature changes in response to its surroundings. So Newton's law of cooling states that the rate that an object warms or cools occurs in direct proportion to the difference between its own temperature and the temperature of its surroundings. Specifically, Newton's law of cooling states that the temperature F of a cooling object at time t is modeled by f of t equals ab to the t plus c for some constants a, b, and c, where b is between 0 and 1. So let's take a look at an example of how we would use Newton's law of cooling to model the temperature of an object. A cup of soup has a temperature of 180 degrees Fahrenheit when served to you. After sitting out in a 71 degree Fahrenheit room for 5 minutes, the cup of soup is 170 degrees Fahrenheit. Let f of t represent the soup's temperature in degrees Fahrenheit at time t in minutes, where t equals 0 corresponds to the time the cup is served to you. So we know from Newton's law of cooling that f has the form f of t equals ab to the t plus c for some constants a, b, and c, where b is between 0 and 1. And so we're going to first, in order to find a model for this situation, we're going to think about the soup's long-term temperature first. So if that cup of soup were to sit out for quite a long time, eventually it would reach room temperature if we didn't touch it. So the long-term temperature for the soup would be 71 degrees Fahrenheit. Right? And then we're asked, what is the long-term value of f of t? So here we have f of t. What's the long-term value of that? And we know from previous knowledge that f of t is going to tend towards the value of c as t increases without bound. So what can we conclude if we put these two things together? We know that the soup is going to approach 71 degrees Fahrenheit in the long term, and we know that the function f is going to approach c in the long term. So ultimately what that tells us is that c equals 71. All right, so we now know what c is. We'll work next to find the value of a. So this just restates the problem. We already know the form for Newton's law of cooling, and we just determined that c equals 71. So now we're ready for part B. What is the numerical value of the soup's initial temperature? Well, we were told that the initial temperature is 180 degrees Fahrenheit. And then next we're asked, what is the value of f of 0 in terms of a, b, and c? So if we were to take f of 0, here's f of t, so we'd have ab to the 0 plus c. We know b to the 0 is 1, so we would get a plus c. And we also know that when we find f of 0, that's just another way of saying what is the initial value, or what is the initial temperature. So if we put these two observations together, we know that a plus c needs to equal 180, and then we knew that c was 71, so a plus 71 needs to equal 180, which tells us a equals 109. So lastly, we can put all of this information together If we know that B is approximately 0.981, we're going to use our work to determine a formula for f of t equals ab to the t plus c. That models the temperature of the soup as a function of time. So all we need to do is replace A with 109, B with about 0.981, and C was 71. In future lessons, you'll learn how we found that B value, but for now you can just accept that it's approximately 0.981. All right, so let's use this model now for the temperature of the soup to explore the average rate of change of the temperature of the soup and what it tells us about how the soup's temperature is changing. So again, this is just what we know. F of t equals 109 times 0.981 to the t plus 71 represents the soup's temperature at time t minutes, where t equals 0 corresponds to the time the soup is served to you. So we're going to determine the average rate of change of f on the intervals from 10 to 15, 15 to 20, and 20 to 25. And then pretty standard here, write at least 2 careful sentences that explain the meaning of the values you found, include units, and discuss any overall trends. So I'll give you a minute to go ahead and find the average rate of change. I know you're probably getting pretty good at that. And then we'll work on the sentences together. All right, so the average rate of change from 10 to 15 was approximately negative 1.6499. From 15 to 20, the average rate of change is approximately negative 1.498. And from 20 to 25, the average rate of change, you should have found it to be about negative 1.361. So the first sentence we could work on would be, let's just explain, for example, what the average rate of change from 15 to 20 represents, right? So we know that the soup's temperature is decreasing, right? And we know it's decreasing because of that negative, right? We want to mention at an average rate because we're finding the change in temperature, or the rate of change over an interval. So this is an average rate. The soup's temperature is decreasing at an average rate of 1.498. I don't need the negative because I already said decreasing. My units would be output divided by input. The output was degrees Fahrenheit. The input was minutes, so degrees Fahrenheit per minute. And then we want to mention an interval because, again, if we picked a different interval, we see we're getting different values. So the soup's temperature is decreasing at an average rate of 1.498 degrees Fahrenheit per minute within 15 and 20 minutes of being served. So there's one sentence just explaining one value of the average rate of change. So the other thing we want to do is make sure one of our sentences discusses the trends in the average rate of change. So what are we noticing in the trends here? So we notice a couple things. We notice that the average rate of change is negative, and we notice that the average rate of change is increasing, right? These values are getting less negative. So we've seen previously that if the average rate of change is negative and the average rate of change is increasing, that tells us that the function f of t is decreasing slower. Another way to say that, f of t is decreasing at an increasing rate. If we were to graph f of t, it would have a shape something like this. So the graph is decreasing but slower, or we say f of t is decreasing at an increasing rate. So in context, our actual sentence, we could say something like the temperature of the soup is decreasing slower. Or the temperature of the soup is decreasing at an increasing rate.